Hi everyone, hope you are enjoying this conference here in Bern. Today I will be presenting chemical stabilization as a solution for underliner cobarrier and structural layer for landfill cells in granular soils. I will take a case of a study that is sand stabilized with SS21 polymer, that is what I have here. I will circulate then this sample. What we are doing here is just taking in consideration the hydraulics and structural properties needed for a landfill cell barrier, working at the same time with the geotextile heat. So, I will start from scratch because maybe some people not need to know what chemical stabilization is. So, chemical stabilization is basically the use of chemicals to create a compaction aid, a particle binder, or water repellent, or many of these properties in the soil. This can be applying chemical and water during compaction or by spray. So this gives us two possibilities: to do a volumetric application, that means mixing the chemical with the soil and water. That is what we usually consider as stabilization. So that's what's called in the industry stabilization. Also, we have superficial application, that is basically spray over a surface and create like a coating. And that's what in the industry is known as dust control. So here is a definition. So basically, this chart is a summary of this definition explained more easily. As we can see, there are various types of soils. Mainly, we have two big groups. One is clays and silts that make the cohesive soils, always talking about inorganic soils. So cohesive soils are basically clays and silts, that are small particles where the magnetic electric forces between particles are the main phenomenon. And then we have granular soils like sands and gravels, where the main forces acting are the gravitational. So this is the approach we took because we were working on cohesive soils, and we find out that the chemicals produced for stabilization of cohesive soils doesn't fit well in granular soils because the physics behind it is different. So we started from a kind of phenomenological approach, and we say we have to think the problem different. So that's why we started with the development of this chemical product, a different solution based on the same principle of chemical stabilization, but doing a different approach. So basically, granular soils can be obtained or classified by different methods. The first method is more used for roads or for civil engineering. This is soils A1 to A4 are mainly, not A4 is the limit, but A1 to A4 are the granular soils. In the second case, that is more agricultural type of classifications, we are talking about sandy soils and gravelly soils. And the third classification is the type of unified soil classification system that is mainly used in geotechnics for foundations, for example. So we say gravels, sands, and in some cases we can talk about silts. Why granular soils? Because granular soils have several properties that are in some sense complex or problematic for the use in geotechnical applications. In one case, we have permeability. Permeability in granular soils is usually high, so it leads to a lot of seepage. That's a big problem in for example, water transport and some other applications. The unconfined strength is low in granular soils. That's what leads to surface erosion. So in every granular soil, you can see when it is exposed, it tends to disgregate. So that's what means with unconfined strength. No strength at superficial level without confinement in depth. Airborne particles. So loose particles in granular soils create a lot of dust. That's another problem in many applications. So as we can see, also is an erodible soil because of this, what we say before. So it leads to volumetric erosion. So there are a lot of problems and complexities with granular soils in engineering practice. What's the practical solution? If based on granular soil physics, instead of forcing the solution we have in cohesive soils, that is to work in the microstructure of the particles, we change the approach. We use the same, and we are here to show that chemical stabilization is a good approach for this kind of problem. But in this case, we need to go to another type of solution. So the physics of the soils are different in cohesive and granular. That's why the premise of the hypothesis and the starting point for our design was to create particle bonding, to improve the strength, and to create a waterproof material, even in surface or volumetrically. So that's why we came out with this development. So now that all knows more or less what chemical stabilization is, I will circulate this. This is a sample. This is a sample of sand stabilized with this chemical, and can be with any other soils in chemical stabilization type of solution. You will see something like that. Sand that usually makes a stockpile. You can't mold this just with sand or water. So I will circulate this sample. So basically, what you can see there is the sample of sand gets strong. So how do we use a chemical for stabilization? We use it superficially, applying by spray, so like creating a coating, or we use it volumetrically, mixing it with the soil, and we create a layer. Those are the main topics we will talk later for creating a barrier in a landfill cell. So this, as you can see in the top photograph, this is a superficial demonstration in Texas, in Isla del Padre, and below another demonstration in Texas as well, but in Midland, a volumetric application. So basically, superficial application is diluting with water, and you spray it, and you create a waterproof non-structural layer. But in volumetric application, you mix it with the soil, like in any earthworks, and you create a waterproof and structural layer. That's what's important for us in landfill cell geobarriers. So this polymer was developed by the authors, and what we did then is doing a lot of testing, because we need to prove that it can stand there for years and years. So we focus on two main key properties, groups of properties: structural properties and hydraulic properties. Structural properties, compressive strength. As you can see, these are the type of tests that are usually done for this kind of uses. As you see, the improvement is great. These percentages are as a percentage of the optimum moisture content. That is the water that the soil needs to get to its maximum density. So really, it means around 1 to 2% of the total volume of soil. So it's a small amount of product you need. Really, these are the standards used, and these are the tests. And the improvements are in 3 digits, in most of the cases in percentage. So we have a lot of unconfined compressive strength improvement, good compression, and CBR ratio. So the properties in compression are getting much higher with the use of chemical stabilization. Well, flexural and tensional strength is measured by, in this case, we use 2 types of tests: beams, mortar kind and concrete type beams, and Brazilian testing strength, that is basically a cylinder diametrically loaded. And as well, the properties are increasing in high amount. So we can say that it is structurally stable and has a property that is hard to find in any soil or chemical improvement, so in traditional ways of improvement. So that's why we are showing these results. And then the other key topic is permeability. For this case, impermeability, what we did is we took, for the previous case, all the tests done are in sand, in a sand like sand you are seeing in this sample. So it's a sand like a beach sand, kind of sand from Argentina. So it's a clean sand without fines. And going now to permeability, what we can see is two cases. We did two cases. One is 100% of this sand, and then in another case we did 80% sand and 20% clay, just to simulate a more real condition of soil, because usually the soil has fines. What we obtained really is the compacted sand. We took as reference the soil in the condition, the original conditions, but just compacted. And we did permeability tests under load and in different variants of these tests. You can see the standards. And basically what we obtained is a considerable reduction in the permeability coefficients of the soils using chemical stabilization. So with that, we can see that with the use of the product and another variant of the product, we can get to semi-permeable and impermeable layers. So that's what we are looking for when we talk about the geobarrier, and when we need to prevent the infiltration of water or any liquid we have in the landfill set. In this case, the liquid is much worse than water for sure, but when we need to get impermeabilization, we need these coefficients kind of values. So this is a typical geobarrier landfill cell. As you can see, there are semi-permeable soils and impermeable layers. We take 10 at -7 at impermeable, and we have several geotextile membranes. And there are many conformations and many types of layers that can be used, but basically what we need is to get impermeabilization. So this impermeabilization is proved in the test we see before. And the geotextile layers are needed anyway, but we can replace the use of bentonite, for example, or other materials that are usually hard to be used in this application and requires a lot of volumes. So using chemical stabilization, basically we are independent from any soil on any site. Basically in granular soils where the need of bentonite is really high in percentage of replacement. So basically we have these structural requirements that we were talking before for embankments and roads that can be the perimeter of the landfill cell, or the roads that are the access to the landfill cell. We have this need for stability when soils are granular. And the slope angle as well in granular soils is, as we can see, creates a lot of need for volume in earthworks. Compressive and tensile strength and erosion and dust control are also main structural properties needed in these cases. As we shown before, the properties are met. And also earthfill cells layers that we were talking before, the key or the critical element. What we need is bearing pressure, controlled settlements, and controlled volumetric erosion as well. And that's as well improved and show as we shown before. So the requirements are met to do this kind of application with chemical stabilization. Basically, the summary of the advantages of using chemical stabilization instead of other types of stabilization or other methods are to use the available soil on site. It means a reduction, an important reduction in earthworks, in transport. You don't need to import soil. Is site-independent project mean that you can do this in any project, just classifying the soil and getting some properties from the soil. You just then use the chemical, and you avoid the need for bentonite. That is hard to work with and usually requires a lot, and you don't always have just that on site or near the site. The product is eco-friendly. You can use it liquid, store it, and as well the properties as we saw before are met, and we have engineering properties in this case shown. So basically this is as a summary, we can say that a chemical stabilization is a proper solution for landfill cells. These are examples of this particular sample that I'm circulating across the audience. So you can see these cases are similar to the tests developed on lab, but it's much easier sometimes to see it this way. The first one can be a Brazilian test. The second one can be a compression test. The third one, it was a saw cut. So we cut it with a saw. And then the other impermeability tests like commercial. This is kind of for showing, no? And this is, and then another application for showing how it is stable underwater. So hope you enjoyed the presentation, and thank you so much.